So the learning objectives here are describe what resonance means in Lewis dot structures. We're getting a sense of, for that nitrate anion, where does the double bond go if there's three equivalent places to put it? And identify fractional bond order and describe what that means that's closely tied into resonance, and calculate formal charges and use them to predict the most stable Lewis structures. This gets into, does the double bond form with the chlorine or does it form with the oxygen? All right, so let's dive in. Consider ozone. Let's try writing the electron dot structure for ozone. So let's see, it has just, they're all oxygens, so 3 times 6 equals 18 electrons. And we see here that we've got 2 in bonds already for them to connect to each other. That's 14 electrons we have to place. Okay, let's start putting them on the periphery. Okay, that accounts for 12, so we can do 2 more. You know, that doesn't look so great because, let's draw these in a little darker so they're easier to see. Although we've used up all 14 electrons, we don't have a complete octet on the middle oxygen. So we need to take 2 of these lone pairs and, or one of the lone pairs and make a double bond. So now they all have a complete octet. This one on the side has 2 lone pairs and a double bond, so that's 4 electrons around it. The one in the middle, 3 bonds, 2 lone pairs, that is also full octet. And then on the right side, we've got 3 lone pairs and 1 bond, that's a full octet there. But on which side does the double bond go? You could imagine, you know, this structure here, which is what we have. And, you know, you've also got this structure here. You've got this structure here, where we've got the double bond over here. Now, both of those are just as good as the other one, right? There's nothing to say one picking the other, and they're equivalent. So could we just say that, you know, there's just one structure. It's just the structure where you have a double bond and we can't really tell the difference. But it turns out that something deeper chemically is going on, is that you actually could, what it is, it's a superposition of both of those. So there's this concept of resonance. When it's possible to write down more than one electron dot structure, the actual structure is an average, a blend of all of the possibilities. We call this resonance. It's not bouncing back and forth between the two. That's what you would imagine with something like resonance. It's not bouncing back and forth. It's a superposition of the two. It's half of one, half of the other. The structures that come out are resonance hybrids. So if we actually look at chemical information from ozone, a double bond on average is about 121 picometers. It's closer than a single bond. The atoms are bound more tightly, so it's closer in. A single bond is 132, and ozone is right in the middle. It's right between them. It's not as strong as a double bond, but stronger than a single bond. Same thing holds if you look at bond strength. So an oxygen-oxygen double bond has 498 kilojoules per mole. Approximately, an oxygen-oxygen single bond has 146 kilojoules per mole, and an ozone bond is in between the two. And so it's an average of these two structures. And so is it a single bond? Is it a double bond? No, it's an average of the two. The average bond order is 1.5 because you have 2 resonance structures. It's a hybrid between a single bond and a double bond. So sometimes it's drawn like this, you know, why that triangle shape we'll get into more when we talk about molecular shape. But that is, the bond order is not 1 would be for a single bond, 2 for a double bond, 1.5 for the bond in ozone that is a superposition of 1 single bond and 1 double bond.